All right. So welcome everyone. Happy New Year. I hope everybody had a enjoyable and safe holiday and prosperous and happiness for this year. So we're continuing with our webinar series, and today's presentation is on roofing and issues and why we picked this topic. It's been a hot topic for us to discuss about roofings and slants of roofings and ventings of roofing. So I reached out to our to Trevor Trainer, who this is really his areas of expertise, and to give us a little more insight on roofing. So I know Trevor. We just taught a week. Uh, Working together, and he's been given lots of presentations from coast to coast to coast. So I probably best that Trevor can introduce himself better than me. So I'll turn it over to you, Trevor.
Oh, you're muted,
Yeah,
Trevor.
I see that now. Okay, now I'm back. Thanks, John. Thanks, Christine. Happy New Year to everyone and welcome. Thanks for joining us today. My name is Trevor Trainer. I'm a member of the Thessalon First Nation and the president of Boating Building Science, which is a building science consulting firm that I started about 2 years ago to focus on Indigenous housing issues. Today I'm going to talk from sort of a more technical side about roofs in general, and more specifically about ventilation of roofs, when we have to ventilate, when we can get away without ventilating, some of the issues that I've encountered over my years of forensic investigations, investigating failed roofs and some of the causes that we've found for these failed roofs. So let's see. Oh, don't stop sharing. Okay. I'm gonna figure this out. There we go. So in general construction, we talk about roof systems. They're usually and a commercial roof. And a residential roof, are the ones that probably you're 99%, most used to, which is an attic space that's ventilated. There's probably intakes at the eaves and vents at the peak or near the peak. They're simple roofs, they're sloped, and they're vented. And then the other thing we see on the
Trevor, just interrupt. Trevor, undo your turn your camera off because you're breaking up a little bit.
Oh, okay. Let's try that. Okay, let me know if that helps at all, or if there's anything else we need to do. Okay, great.
Perfect. Sorry, guys.
Okay, no worries. Then the other type of roof we see in the industry, not in residential, but more commercial, are these flat roofs that you see everywhere. Like every warehouse you see has a flat roof. These are obviously simple roofs. They're flat and they're unvented, and they have a very good track record of working also, right? So both of these systems have worked really well for us over the last, probably 100 years of construction in Canada. Now things are getting a little more complicated because we're starting to see these types of roofs residentially, these sort of mixed things that are partially flat and partially sloped. They're much more complex. And because they're residential, and we have residential contractors working on them and residential designers designing them, we have been trying to ventilate them, just like we did before with our sloped roofs. And we're seeing some specific issues from that, and we'll talk a bit about why that is. So to really understand ventilation in roofs, we need to understand air movement in buildings. So for air leakage to occur in a building, we need two things. We need a pressure difference across the building enclosure, and we need, sorry, there we go. Let me just pull that right out. Okay, so we need a pressure difference across the building from inside to out, and we need pathways for that air to flow. So if we have no holes, we'll have no airflow. If we have no pressure, we'll have no airflow. But in reality, the buildings we build do have holes in them, whether we like it or not. And nature tells us that we always have pressure differences. And we'll talk a bit more about that and how they affect airflow in buildings. But it's important to know that we need both of those things, a pressure difference and a hole, in order for airflow to occur. Not just from inside to outside, but also within the attic, which we'll talk about. So when we talk about pressures on buildings, we tend to first think about wind pressure, because that's the most obvious one, and it's also the most sort of dramatic one. So wind pressure is a function of obviously wind speed, as well as building geometry and local topography. Is your building surrounded by other taller buildings? Is it out on its own, being exposed directly to the wind? Are there wind tunnels created by tall buildings in the area? When we talk about wind pressure, the peak pressures we're talking about can be really high, up to 300 pascals of wind pressure that we could see in peaks. But it's also, these peaks are really important structural perspective. We need, our roof to stay on, our cladding to stay attached during these peak wind events. And also important for rain penetration, right? If those high peaks happen with rain events, then rain penetration can really be affected by those really high peaks. But actually, when it comes to roof ventilation, wind has less of an effect than you'd think. So the average pressure really for wind is only about 1/10 of what we get for stack effect in cold climates. And I'll talk a lot more about stack effect next. So if we're looking at sort of the average pressure caused by wind, it's actually a lot less than we'd think. So wind isn't all that important for energy analysis or for natural ventilation strategies, because we can't rely upon it as a significant contributor to attic ventilation. It occurs at some times, but we have no control over it. We don't know when it's coming. If we design a building, we don't necessarily know how much wind it's going to be exposed to. So it's hard to design roof ventilation counting on wind. So that brings us to stack effect. So stack effect is the other pressure that's really important when it comes to buildings in general and when it comes to ventilating attics and roofs. So stack effect is a pressure that's a function of the temperature difference from inside to outside and the height of the building. We'll talk a bit more about that in a technical way. So stack effect is a result of the varying density of air at different temperatures. So like a hot air balloon, you put hot air in a balloon, it wants to rise up. When we have warmer air inside our house, inside our building, than we have outside, that air wants to rise up and leave through the roof. So for example, air at 20 degrees Celsius has a density of about 1.2 kilograms per meter cubed, whereas air at minus 10 degrees has a density of about 1.34 kilograms per meter cubed. So this difference in density creates pressure inside our building because that air is trying to escape. And what that equates to generally is something around 3 pascals per floor. So in a 2 or 3 story building, you're looking at probably about a 6 pascal pressure trying to escape out through the roof and trying to get drawn in through the floor. And so the interesting thing about stack effect is it isn't all just outward. It's outward at the top of the building and inward at the bottom of the building. And so holes we have at the bottom can allow air in. Holes we have near the top of the building can allow air out. And what happens right in the middle, we call the neutral pressure plane, is there's a point in every building where stack effect is 0 because we're switching from that inward pressure to that outward pressure. So when you hear the term neutral pressure plane, that's that exact spot where that happens. And that isn't necessarily halfway up the building. It depends on the distribution of the holes in the building. And sometimes we use that neutral pressure plane, if we can measure it, to diagnose where the air leakage is occurring or where more of the holes are in the building enclosure. So now we're going to talk primarily about vented roofs, like those classic, residential roofs that we talked about, and why they usually work, but why sometimes they don't. So now that we know about stack effect, right? We know that our building, we've got in the winter time, if it's -10 outside, we've got about six pascals of pressure trying to push air out the ceiling plane of our building and into the attic, right? So we also have just heat loss. Even though we do our best to insulate roofs, there's still going to be a certain amount of heat loss occurring through the attic insulation. And the attic space itself is always going to be a bit warmer than it is outside. And that'll come into play in the next slide. So if we have no air leakage, we have a perfect air barrier, we have no problem. We don't even need ventilation because we have, no moisture in this attic to deal with. But the reality is we do have, despite our best efforts, holes in this air barrier. And we do have air being pushed from inside the building into our attic. And so now, instead of it being, almost outside, -8, now it's warmer, say -5 degrees in the attic. And we also have the moisture in the air in the building that's flowing into the attic. And what we typically see, and you've probably seen this, if we have a large amounts of air leakage, you start to see condensation, mold growth, etc. And it usually starts on the underside of the plywood, usually near the peak of the roof. And so that's the kind of thing we're dealing with. So if we had no ventilation in this attic, we would quickly have moisture accumulation. We'd quickly have mold and rot of this. It'll start with the plywood and eventually get into the trusses and the roof structure. So that's why in this type of a roof system, we need ventilation. And when it comes to ventilation, we also have the benefit of stack effect again, right? So it's not the same pressure levels we're seeing, but if we have, let's say, because of heat loss and air leakage into the attic, it's -5 in the attic when it's -10 degrees outside, that still gives us a 0.5 pascal pressure difference from in the attic to outside. And so when we purposely put ventilation holes near the peak and near the bottom, we get natural flow of air in at the bottom and out at the top due to this pressure difference that's been created due to stack. So stack effect, even though it's hurting us inside by pushing air into the attic, it can help us in our attic. And so even without wind, right? So remember we said wind can help with this, but sometimes we can't count on it. We don't know when it's going to be windy. We don't know which direction the wind's coming from. But this stack effect is only based on temperature difference and height. So it's always there to help us ventilate our attics. And so really it starts to come down to whether we have moisture problems in our attic or not. It really comes down to a moisture balance. How much moisture are we adding to the attic through this air leakage through the ceiling plane versus how much moisture are we taking away from the attic through ventilation? So it really is this balance, and the more air leakage we have from the building into the attic, the more ventilation we need, and vice versa. So what if we take that same approach and we put it on a flat roof like this? So if you can see this photo, these three little black squares on each of these is an attempt to ventilate this attic space. They're treating it like it's that sloped roof we just saw. But what's the problem with that? The problem with that is we don't have very much at all, or maybe I really don't have any stack effect in the attic to help us ventilate. We have stack effect in the building that's still putting that warm, moist air into this space, but we don't have the benefit of stack effect in the attic to drive that air out, that warm, moist air out. And we start to see accumulation because we don't have a height difference between the ventilation intake, and the ventilation exhaust. So again, it all comes down to a balance. So moisture levels in any vented attic are a function of the ceiling air leakage rate, the attic ventilation rate, and how much interior relative humidity is in the building. And so those are the three factors that we can sort of play with in construction and in design to try and make sure that we don't have problems in these vented attics. Real quick, just look at some of the code requirements and why some of them don't always deliver what they need to. So I don't know, you're probably familiar with, this is from the OBC, I think, but it might be, I think it's the same reference in the NBC. But talking about roof spaces and required venting, it says, except where it can be shown to be unnecessary, where insulation is installed between the ceiling, you know, blah, blah, blah. Vents shall be installed to permit the transfer of moisture from the space to the exterior. So there's always that exception, right? Except where it can be shown to be unnecessary, which typically doesn't get used, but we may want to, you know, think about that exception sometimes. And when we get down into the more explanatory parts of the code, one thing they explain about that is it says that in some specialized ceiling roof assemblies, such as those used in some factory built buildings, so sort of what I showed you as that commercial roof, they have over time demonstrated their construction is sufficiently tight to prevent excessive moisture accumulation. So it is recognized in the code that it's possible to not ventilate. These are rarely sort of used in the code, but it's also, I found it interesting that the reason they chose to accept that is because there's just a track record that these work, not that there's really that much science to explain it. I would prefer to go the opposite way and look at the science side of it. And then vent requirements. Probably most people know that there's sort of two in the code. There's two levels of ventilation requirements depending on a couple of things. So except as provided in sentence 2, the unobstructed vent area shall not be less than 1 out of 300 of the insulated ceiling area. So that's most of our roofs. So as long as the vent space intakes plus outputs are 1/300th of the total ceiling area, that meets code, except as provided in sentence 2. So what sentence 2 says is where the roof slope is less than 1 in 6, or in roofs that are constructed with roof joists, the unobstructed roof vent area shall not be less than 1 out of 150 of the insulated area. So this is a part of the code I have a bit of a problem with, because I think they basically just know that we need more, the lower the slope of the roof is, the more ventilation you need. But they really just took a really gross stab at saying, well, let's make them put twice as much in, and hopefully that works. But as we know from before, there's other factors that can really play in here, and this may not be sufficient for some lower slope roofs. So I'm going to show you a case study now of when a vented roof fails. So this is the type of house that I sometimes work on in Toronto. This is very common design approach for some reason in some neighborhoods in Toronto. So this is a residential roof. This is a vented roof, but this is just the roof section up here. There's no overhangs on the roof. There's like an integrated gutter system behind this little parapet wall here. There's a really steep pitch at the perimeter and a flat section of roof at the top. The other thing that's really important in this case study is that there's ductwork in the attic. And I'll show you a picture of that. And it's covered with open cell spray foam. So what is supposed to happen in this attic is that air is supposed to come through these really small vents, and I'll show you a photo of them, that are lower down on the steep part of the roof and exit through these larger flat vents on the top. And so if it worked properly and we didn't have too much air leakage, you know, this could work. But in reality, it did not work. So what issues did we see? First of all, it started off with water staining on the second floor ceiling after a long cold spell ended and there was sort of a warm spell. Here's some photos I took going in after it got colder. Again, you can see a lot of frost near where the sloped ceiling meets the flat ceiling. Excessive amounts of frost buildup and water staining. This is one of those vents that's near the lower section of the sloped part of the roof. And what I can tell from this crazy frost formation here is that air isn't entering through there like it should be. It's actually exiting through there. So there's something else that's pressurizing the attic enough to overcome the stack effect that is there and pushing air out through these really small vents. They don't have nearly enough net free area anyways, but also they're not bringing in fresh air. So we did a quick ventilation analysis. So how much ventilation was there? Turns out that there was sufficient high ventilation to meet code. There's insufficient low vents to meet code. So that was the first thing that came up as an issue. Probably the bigger issue, though, is this ductwork. So there's basically ductwork in the attic that is covered by this open cell spray foam. It was not installed in an airtight manner. As you can see, there's one example of gaps and holes in the spray foam. And basically every time the heat kicked on, at least some of that air was leaking out into the attic. And that's why we're getting positive pressurization in the attic and ventilation even outward at the low vent positions where there should be intakes. Also, we found significant amounts of air leakage at the ceiling plane in this particular building. So how do we fix it? What do we recommend? First thing we needed to do is air seal the ductwork in the ceiling plane, much better. And so the ductwork was sealed from the inside with a spray applied misting air sealing system. The attic floor was sealed by uncovering all the pot lights. There were many, and resealing them. They also installed about twice as many low vents in the attic. And the other thing we did, because of how much moisture had built up in the attic, was temporarily installed an inline fan in the attic. And this inline fan is drawing cold air from outside and power venting it into the attic to pressurize it with cold air from outside, whereas before it was being pressurized with warm, moist air from inside. And that was done temporarily to dry it out in the meantime. And so once it was dried out, this was removed. We rechecked all of the air tightness improvements and that they added the low vents. And so far, there have been no issues since that was accomplished. So just in summary, for residential vented roofs, the benefits is they can work in any climate. They're cheap and easy. We know how to build them. We can fill them with lots of loose fill insulation. Which is cheap and easy. We can use our polyethylene air vapor barrier, which is a common approach. The trades are really familiar with all of these methods. They can tolerate a certain amount of air leakage to reduce moisture, and they can dry out once the weather conditions allow. So if you can get away with some moisture accumulation in your attic, as long as it does not too much so that it can easily dry out. Once the weather gets warm, the sun hits it and can help dry it out. So those are the benefits of our vented roof systems. But what can go wrong? Too much air leakage. So if we have too much air leakage from inside the house into the attic, due to pot lights, attic hatches, overpressurization of the building, or as we saw, ductwork in the attic, that can be a problem that ventilation can't deal with. Not enough ventilation. So either not enough free area near the eaves or at the peak, or the slope of the roof is too low, so we don't have enough stack effect to help drive that ventilation system. We also see a lot of ventilation blocked by framing and just dead areas of the building where you can't get proper ventilation in. And then other sources of moisture are also something that can go wrong. As we mentioned, like HVAC ducts in the attic, never a good idea. Rain or snow penetration, obviously, going to be bad. And high interior relative humidity. If the house is running at over 40% RH in the winter, that's going to mean the air leakage that is there is going to drive a lot more moisture into the attic than if they were maintaining, say, 30% RH in the winter. So those are the things that can go wrong. Now we're going to talk about unvented roofs for a bit, why they usually work and why they sometimes don't. So these are some of the reasons to consider using an unvented roof. And when we get into really complex roof lines that make ventilation difficult, if we want vaulted ceilings, right? If you want the interior to be vaulted, we're losing that attic space and ventilation becomes much less effective. We talk, low slope or flat roofs, definitely we want to consider unvented roofing. And if we are going to put ductwork above the ceiling level, we might want to consider an unvented roof above that ductwork. So why they usually work. So when you see, the hundreds and thousands of warehouses across Canada with flat roofs on them, this is how they're built, and they tend to work really well. And basically, in this case, you've got your structure, which is this corrugated steel. They put basically an air barrier on top of the structure, on top of the steel, and then insulation on top of the air barrier, and then your roofing membrane on top of that. So in this case, this is non-permeable insulation, right? This isn't fiberglass. This is rigid foam. So we already have our air barrier that's continuous. We have a continuous layer of insulation, and then our continuous water protection layer. This works really well, especially in just a flat situation like this. This same approach can be used on the slope, which I'll show you in a bit. The major thing we have to worry about in a roof like this is penetrations and transitions. So for example, every roof like this has to come to an end at the wall. What do? A lot of times we have these parapets and things start to get a bit complicated. How do we maintain air tightness at this level under the parapet? This is a really common problem in commercial buildings, is air leakage into the parapet. And obviously the parapet itself has cold on almost all sides of it, and moisture accumulation inside the parapet wall can be a real issue. So maintaining the air barrier under the parapet wall is really important in a design like this. And then obviously things that penetrate through, there's always vents, plumbing vents, HVAC vents that penetrate through. How well are they air sealed? And how do we prevent that warm, moist air from inside from getting in and depositing its moisture? So those are the real things to be aware of. Otherwise, this roof system is just very simple and it works really well. But when we start to apply this to residential systems, nobody, I'm not going to say nobody, almost no home builder is going to build a roof system that has all the insulation as rigid insulation on the outside. And so what we start to see, are even in sloped roofs or flat roofs, when they're compact, there's a couple different ways to do that. And this is the not recommended way, just to show you that first. This is also probably still the most common way it's done. And that is treating it just like you would a wall. So you have your polyethylene air vapor barrier, you have batt insulation or blown in fiberglass or something like that, and then your plywood and roofing on top. And so in this situation, it's really difficult in this to make the air barrier good enough to not allow moisture in here, right? Because now there's no more ventilation in this space. Any moisture that does come from the warm air inside into this space is pretty much trapped and is going to accumulate quickly. There's no insulation. All the insulation is interior to the structure. So this sheathing is always really cold, and that's where your condensation is going to form. And that's where you're going to start to see moisture accumulation and rot occur. And their insulation won't stop the airflow. So we're only counting on this polyethylene sheet. And we've got mechanical penetrations. We've got a lot of areas that are difficult to seal. And this always, especially in cold climates, will eventually rot out and become a problem. So that's why it's the one that's not recommended. And I'll show you some alternatives that we can recommend if done properly. So this is sort of like the commercial one. And that's by, the putting 100% of your insulation exterior to the framing. And again, using, rigid foam board that's not susceptible to air leakage. There's multiple air in this system. There's multiple layers acting as the air barrier, so it tends to be very airtight. It's easy to make this air barrier continuous, this green line, because it's put on before the insulation. It's done on the outside of the structure. You can tie it into the wall air barrier really well at the walls, etc. Since all the insulation is exterior to the structure, this sheathing layer here is actually really warm, so we don't have to worry about condensation here. And it's really difficult for air to get to this exterior sheathing level layer because of all the air tightness layers in the system. But again, we still have to beware of penetrations and transitions through here and make sure that they're kept airtight to avoid issues. But this is definitely the most bulletproof way to do an unvented compact roof, whether it's flat or sloped. This is the safest approach, although very rarely used because there are cost considerations with this. And I'll show you some sort of hybrids that work really well that are a little less costly. So this one we call the split insulated roof design. And in this case, we are putting a certain amount of batt insulation between the structural members, so between our joists, but we're also adding rigid insulation on the exterior. And so in this case, if we put the right amount of insulation exterior to the sheathing, we can keep the sheathing warm enough to avoid condensation. So if there is air leakage through here and it reaches the sheathing's warm enough that there is no condensation. And we can still put our air barrier on the outside of the sheathing, making it easier to make it continuous. The really important thing in this system is the ratio of insulation that's, the batt insulation between the studs or between the joists and the rigid insulation on the outside. We have to make sure that there's enough exterior insulation to keep this sheathing warm enough to avoid condensation. So there's a bit of science involved in that, and it depends on a couple of things. It depends on climate, where you're located, and it also depends on what you expect the interior perspective. And again, in any system, we have to watch and detail our penetrations and transitions really well. But this can be a really safe alternative for an unvented roof. That's sort of a hybrid between the not recommended one that had only insulation between the rafters and the one that has all insulation on the outside. We can do a split insulated approach, and it can still be really safe with the right insulation ratios. This one's probably the most common one I see. I think just because it's so easy to do for the builders, and that's just spray foam approach. So in this case, would be closed cell spray foam. And in this case, the spray foam was acting as the air barrier, the insulation, and the vapor barrier all in one. It is really important in this approach that the spray foam is continuous and sealed, and that all areas that aren't covered with spray foam, like doubled up rafters, have to be sealed separately. In this case, all the insulation is interior to the structure. So we have to make sure we don't have any air leakage here. So it has to be really an airtight application of spray foam. I have the clients that do this that I have, my job is typically to review the installation. And what I typically do is pull a negative pressure on the building and look for air leaks with an IR camera or with smoke pencils, and make sure that they fix all the little air leaks through the spray foam and around the spray foam before they close it up with drywall. So this can work really well, but there are some specific caveats to that, in that the spray foam installation has to be done very well in a very airtight manner, and other air tightness measures have to be taken. This is sort of a hybrid between a pure spray foam approach and the bat approach, what they call flash and bat, where we put a certain amount of closed cell spray foam directly against the sheathing, and then fill the rest of the gap with either loose fill or bat insulation. And again, like the split insulated approach, the ratio of these two insulations matters. We have to make sure that this surface that separates them is warm enough to not have any condensation. Again, the spray foam is acting as the air barrier and the vapor barrier in this approach. Spray foam continuity is just as critical as it was before. And again, the insulation ratio is important too, just like with the split insulated. But this can work really well with the proper design and quality control. And just a note, as I talked about spray foam as an air barrier, I know a lot of people in the industry think that if you use spray foam, your building will be airtight. That is not true. What is true is if you use spray foam and it is installed well, your building can be very airtight. So there's just an example of, and these are really typical examples of air leaks I find when I'm reviewing spray foam. In a rim joist area, this is really common, that the spray foam gun doesn't get quite to the right angle and completely fill the gap. And this is what air leaks look like with an IR camera and negative pressure in the building. And this is how I can identify and have make sure that these are fixed before closing these areas up. And so spray foam can be a great product, but it's really important how it's installed, how it's inspected, etc. So it's not just a cure-all for air tightness. It's a tool that can be used when done properly, can result in good air tightness. And just as an aside, because this comes up once in a while, are SIPS panels for an unvented roof. Typically, especially in cold climates, I don't recommend SIPS panels unless the roof is very simple. So there's a couple reasons for that. We have to beware in SIPS panels, you have to beware of air leakage at all of the joints and of three-dimensional air leakage pathways. So if air leaks from the building into the panel, even out here at the wall, it's going to follow this joint up and start to accumulate near the peak. This has been a real issue in far northern climates of moisture accumulation at the ridge and ridge rot in SIPS panels. It's really important that these are installed very airtight. Also, typically SIPS panels are supported interiorly at ridge vent or at ridge beams, and these can be areas that are really hard to air seal. So it's possible, obviously, to do this properly, but air tightness is really important. The other thing about a SIPS panel is all of the structure is built into the OSB skins. And as soon as there's some rot in the OSB skin, you lose your structural integrity versus a roof that has made out of 2x10s that can rot out probably 25 to 30% before you have a real structural problem. These can become structural issues really quickly. Okay, and then real quick case study. How are we doing for time? Yeah, we're doing pretty good. And this is when unvented roofs fail. This is a flat roof townhouse that had a patio on the roof. And this is how it was built. So in between each unit, there's these block walls. Each unit has its own patio with like this sloped roof on top. And the yellow you see here was originally supposed to be, in the drawings, was closed cell spray foam, but they decided to replace it with open cell spray foam, which created a real problem. And so let me show you what happened. Basically what happened is when they replaced the closed cell spray foam with open cell spray foam, they added a polyethylene vapor barrier, but it wasn't sealed properly at each of these demising walls. And there was a lot of air leakage occurring through there. There's also a lot occurring through these block demising walls. And so what happened was we ended up with a lot of moisture accumulation in the sloped area of this roof and up in these parapet caps. So what did that look like? As opened up, you can see, so here's the top of that parapet wall. And you can see the damage as especially the closer we got to the parapet wall, the more damage, moisture damage there was. As we moved away, it was less. And so you can see this is the piece of poly that was supposed to be sealed to that block demising wall. It was just loose applied. And so you can imagine we got a lot of air leakage up into the system from that. And how did we fix it? We fixed it by turning this into sort of a hybrid approach where we added rigid exterior insulation to the outside. First added a new air barrier in green, then added a rigid insulation that continued up and over the parapet, and then a new roof on top of that. And so there's still, because they didn't want to do any damage to the units from the inside, we still have air leakage probably coming into here, but because we're protected by this exterior insulation, the sheathing is no longer cold enough to have condensation, and there's no more moisture issues with this system. So real quick summary, benefits of unvented roofs. Ideal for low slope roofs and complex roofs where venting is difficult or venting is ineffective. It can be easier to accomplish good air tightness with an unvented roof potentially. We're not relying on questionable amounts of venting for performance. You're basically making sure that the moisture doesn't get into the space. And like you said, they're really proven track record commercially. So when done properly, they work really well. What can go wrong? Spray foam as an air barrier, we have to be really careful. They must be installed with good care. Third-party inspection is always recommended. If we're using an approach with exterior insulation, if we don't use enough for the split insulation or flash and bat system, we can still have moisture problems if we don't use enough exterior insulation as a ratio of exterior to interior. And as always, if we don't detail our penetrations well for water control and for air control, we can still have problems. Now I think I can open it up for questions. If anyone has any, we can take it from there.
Hi, Trevor. It's Claude here.
Hi, Claude.
Very good presentation. Thank you. I have a flat roof on my house, and I learned many, many years ago that in building flat roofs, certainly they can be considered generally problematic. So when I basically did my roof joists, I basically in the opposite direction put 2x4s in.
Okay.
And basically use that as my 1.5 inch, we'll call it a ventilation space right across the entire roof. So that seemed to work quite well. But one of the issues that I found commonly occurs is with flat roofs is when we put the drainage system in. So if we look at a commercial a roof drain on a flat roof, somehow it has to be basically channeled out to the exterior.
Right.
Do you have any good recommendations on what should be done with, let's say that, we'll call it drainage line going to the exterior? Is that something that you would recommend as being spray foamed, or do you think fiberglass insulation would be adequate enough?
So I get, you're asking like, so an internal drain, so when it enters the building, should it be insulated?
Well,
Is that what you're asking, or? Because,
basically, let's take the roof drain on top of the roof that's going to
okay,
drain the water off the roof. Is going to be channeled through that, we'll call it the roof framing system to the exterior and basically dumping it to the exterior. So it's the roof
so
water.
yeah, so we can do that with a scupper, like directly off the roof, or you can do it with an internal drain, which most commercial buildings do, where they have like a drain that brings the water into the building in a pipe and then out. So, yeah.
Yeah, I kind of get that. Again, I guess I'm looking at what's the best way to protect it from freezing in the winter.
Well, water should never be standing still in the pipe, right? Or in the,
Yes.
right? So when it's flowing, yeah, if anything, you would want to insulate, if you're bringing the pipe into your building, you would want to insulate it so you don't get condensation on it, because it is going to be cold.
Yes.
When that water does flow through, and you'll get condensation on the outside of the pipe. And typically, so you can't just do that with fiberglass or something, because it has to be something that's vapor closed. So it would have to be foam wrap or spray foam, or like closed cell spray foam.
Yeah, because some of the conditions in the inspections I've been involved with is sometimes you might encounter cracking in the, we'll call it the ABS plastic piping that was up
Okay.
in that space, and eventually lead to, especially in winter conditions and freezing potentially, leakage into the ceiling.
Yeah, I see that. Yeah, I know
mean,
that for commercial buildings, they always use like iron and or copper for those pipes, maybe for that reason. I'm not sure.
yeah,
Residentially, I prefer to just use scuppers and not bring it into the building and just get it, off the side of the building through scuppers.
okay. Thank you. I think you
That's
pretty much covered what I was trying to get at.
okay. Yeah. Okay.
Thanks, Trevor.
No
I
problem.
have a question from Alan. He's wondering, how do you insulate a dryer vent in the basement?
So if you have a vent coming, you would want to cover it with something that does not allow vapor through. So either you would wrap it in a foam, like a foam rubber wrap. There is, you can also buy like a fiberglass wrap that has a poly or plastic sheet on the outside of it. You'd have to make sure you have at least that, because if you were to just wrap it in fiberglass, you'd still get moisture accumulation on it in the winter. So you'd either want a fiberglass wrap that has a polyethylene or plastic cover on it, or use like a foam rubber wrap that you can either buy in a strip and wrap it around, or they make some that have two halves that kind of clamshell over it. So I think those are probably the two best options.
Great. I don't have any other questions. I do have 2 comments just in the chat. One from Ian, just a comment. He enjoyed the material and found it well presented and it made a lot of sense.
Thank you.
And another comment again from Alan. He said it was an interesting topic and he learned a lot.
Great. Well, I enjoyed talking with you guys today. And if any questions come up after the fact or whatever, you can send me an email. I usually put my email on this last slide, but I see that I didn't this time.
Or they can reach out to me or Claude or Christine. We can forward you. We know
Sure.
we know your email.
Yep. I'm easy to get a hold of. Definitely.
All right. Claude, any further reflections?
Yeah, I really enjoyed the presentation. Very well done, Trevor. You know, I think the case studies really helped me get much more out of it. So thank you for showing us those case studies, because, you know, the text is good information, but certainly the images and the illustrations help reinforce that whole issue of the importance of understanding roofing systems, and certainly moisture migration up into that roof space.
Great, thank you.
Oh, we have a Rudy actually. Just
Hello.
Hello.
Can you hear me?
Yes.
I had just a question for Trevor in regards to, we're talking about the roofing and moisture and so on. What's your thoughts about bathroom fans venting underneath the soffit? Now, over here in British Columbia, we don't have anything that sets a rule that says you can't vent underneath the soffit.
Yeah.
So I guess
I think.
Go ahead.
Yeah.
Trevor.
Just would I recommend that, I guess. I would say that I've never seen an issue resulting from that practice. But on the other hand, it would be better to either vent it somewhere where it can't go back into the attic. So the other option, I guess, is to vent it straight up through the roof. So from a ventilation moisture perspective, that's better. That does add one more penetration in your roof, I guess, that we might have to worry about moisture coming in from the roof. But I think with modern flashing techniques, it's probably a better approach to go up through the roof and get that warm, moist air up away from the intakes to the attic.
And the second part of that question, Trevor, is what's your thoughts on range hood venting in the soffit ends as well? I'm looking at it from a health and safety point of view.
Yeah, I'm not as worried about that because there should be no reason why any air that is in your attic should be coming back down into the building, unless there's some other reason why there's overpressurization of the attic. So I'm not as concerned about that, but again, it's just better practice to get the air that you're trying to get rid of, put it somewhere where it can't come back in your attic. So again, straight up through the roof would be a better approach. But I've never seen any issues occurring from doing it down through the vents or through the soffits.
Okay, yeah, that's basically what I was looking at. I mean, I find that at this end here with up here in Kamloops, we have a situation where I don't like to see it because I do see moisture creeping back into the attic, right? Even though the attic might be well vented, but that particular area, we're usually where the moisture is driving itself back in. Usually, in most cases, wind driven. We get pretty good winds here. We'll have brown spots or even black spots on the plywood on the underside.
Yeah. I've never seen that, but it makes sense that could definitely happen. So yeah, I think when in doubt, poke it through the roof and get it up above the roof and let it go into the atmosphere and not come into your attic.
Yeah. And your thoughts on using, like I see for fans that are being vented up through the attic, I see them using that insulated flex pipe to go through the attic. I mean, I haven't really seen it, but I mean, I've heard from other inspectors that the moisture rolls back and can freeze into that pipe. What's your thoughts on that? Do you think we should use smooth pipe and insulate it?
That would be better for sure, because yeah, those flex pipes, you can only insulate, they only come so well insulated. And there's going to be certain times a year where you're going to get condensation on the inside of that pipe as the air is exiting, and it could roll back down for sure. There's also strategies I know of how that pipe is run, so that if there is condensation, it doesn't run back down in to the fan, but runs outward to wherever the vent is going to. But hard pipe would be easier to properly insulate for sure. And it's just better for airflow too. So
I thank you very much, Trevor, and an excellent presentation. Thank you, sir.
Thank you very much.
Got one more.
Yeah, sorry, I have a couple more questions. One more from Rudy maybe, and then another from Scott.
I think.
Oh, go ahead, Scott.
Yeah, I think Rudy's good.
Hey, Scott.
Oh, 1 second, he's muted. Let me see if I can.
Yeah, might be on mute.
Go, Scott, go. Here, see if I can unmute.
Yeah,
Why can't we unmute him?
yeah, I don't know.
Scott, can you unmute yourself? Turn on your camera and wave.
Oh, there we go.
Okay.
Hey.
There we go,
Sorry,
Scott.
I'm
Awesome.
learning technology here. Okay, so vapor barrier. We all know that it breaks down after a certain period of time, right? So recommendations on timelines or life expectancy of when should a person put a new vapor barrier in?
Well, so there was an issue in the 80s and probably early 90s of polyethylene that if it was exposed to sort of any indirect UV would break down. The modern versions we've been using since the mid 90s don't have that problem. They have UV stabilizers in them, and they shouldn't really be exposed to much UV at all. They should be under insulation in the attic. And so it shouldn't be an issue, but when you're looking at older houses, certainly it does come up that the vapor barrier just turns into flakes. So I don't know of any specific rule of thumb for that, other than maybe just when you have the opportunity to check it. Really difficult thing to replace once without pulling all of the ceiling drywall down. So it'd be a major thing. You may want to consider if it did completely break down on you, you may want to consider like just a 2-inch layer of closed cell spray foam from the top side, as opposed to ripping off all the drywall and trying to replace it with a new poly vapor barrier.
Okay.
Yeah.
Scott, is that a big issue for you guys, or?
No, it was just a thought that crossed my mind here just towards the end of the presentation.
Yeah.
And like, because I know we have like we get moisture in the walls due to vapor barrier and stuff like that. And I was just thinking, well, okay, ceiling, attic, and air movement. I was just thinking like, because of the air movement later on, if it's a blown in vat, the insulation moving and then the constant heating and cooling of that poly, just eventual breakdown. That was the thought that was crossing my mind.
Yeah, it's the UV exposure that can break it down. And, if in an attic there is some sunlight that gets in there, and if there's some exposed because the insulation's moved away, that could be something to worry about. And I know, like I said, in the 80s versions of poly, it was a bigger problem, but modern stuff should last as long as the house.
All right, thank you.
No problem.
Flo, do you have a comment?
Yeah, Scott, maybe one possibility, and I've encountered this before, is taking a look at some of the higher quality paints. If it was a ceiling application, certainly maybe a good coat of paint might help reduce that, we'll call it moisture going up and through the ceiling system. So I've seen systems such as, I think one product name is called BINZ, B-I-N-Z, as being one of those paint types that goes on like a paint, but it has certain characteristics that basically help seal and create almost like a new moisture or vapor barrier.
Yeah, there are vapor barrier paints and primers that are available on the market. Almost every manufacturer makes one specifically that can stop vapor or slow it down. The issue with the broken down poly is not just that it's not just the vapor barrier that's broken down, it's an air barrier too. And so that paint isn't going to do a very good job replacing it as an air barrier. But from a vapor flow standpoint, there are paints and coatings that you can put on from the inside. That is true. Yeah.
Great, thank you.
Well done. Thanks, Trevor. The good news, Trevor's back next week for another presentation on.
I think it's
Again,
I think I'm in 2 weeks, John. I could
Yeah.
double check that.
Yeah, I think